Let's look at a situation where we don't have an object sitting actually on the floor or the ground or the table. But imagine for whatever crazy reason you take a book and you press it against the ceiling. In this particular case, we'll have a person using a force P with a magnitude of 80 newtons at an angle of 70 degrees with the horizontal to push a 5.0 kilogram book across the ceiling. If the coefficient of kinetic friction between the block and the surface is 0.4, the question will be, what is the magnitude of the acceleration of the book? We're going to start with the usual way. In other words, we're going to draw all the vectors here for all the forces acting on this book. So we will draw a diagram, what in physics and engineering is called free body diagram. I like to call it force diagram. Here's the gravitational force, always pointing downwards towards the center of the Earth. And here is the kicker, really, for students who see this problem on tests or quizzes or homework. The normal force, when you draw the vector for the normal force, has to be downwards. Think about it. The ceiling cannot pull that book upwards. The normal force is a force that always reacts. So if we have someone pushing that book against the ceiling, the natural reaction of the ceiling is to respond in an opposite way away from that push. So we'll have the normal force vector drawn downwards. We will also have friction, and it looks like the natural motion of that book will be to slide to the right. So that means that the friction will be kinetic. Remember, whenever we have sliding, that will be a kinetic friction, and the vector for the friction will point to the left. I will need the coordinate system. The most natural choice here will be positive x to the right, and I'll put for positive y upwards. With that, let's go around all the vectors here on my diagram and see what their components are. For the normal force, once again, I will have only a y component, but in this case, it will be minus Fn. So Fn is just that value for the y component, and minus to reflect that the vector now points downwards in the opposite of the positive y direction. For gravity, of course, I will have 0 and minus mg for its components. And for friction, I will have only x component, but no y component. Remember here for the x component, I have written it in terms of minus mu f. And remember, the magnitude of friction is always a fraction of the normal force. How much that fraction is determined by the kinetic coefficient of friction here between the block and the surface, and the problem tells us that that is 0.40. So the only force here that I cannot tell immediately what the components will be is the pushing force P. So I'll just mark its components Px and Py. To find its components, we usually take this vector and draw it on a separate diagram here with the coordinate system x, y that is identical in its orientation to the one for the block. Here's the vector. I marked the angle theta, which the problem tells me is 70 degrees with the horizontal. The way I find the components is by drawing the perpendicular from the tip of that vector to the closest axis. So this is the x-axis, and that's form a right angle triangle here between the vector and its two components. I see that the adjacent side will be the x component of that force, and it will be equal to P cosine theta according to trigonometric rules, and that leaves for the opposite side to be the y component of the push, Py, and it will be P sine theta. So I will be using these facts here so I can actually move them to my diagram if I want. If I wish to have everything in one diagram, I can just go back to where the P is and say its components are going to be plus P cosine theta and plus P sine theta. Notice both components are positive because the vector is directed up and to the right. Up means positive y component, and to the right means positive x component. With that, let's write Newton's second law. Here's the form in here's the vector form, but we're going to jump directly to the relationship between the x components of the net force and the x component of the acceleration. So we're gonna go around those four vectors and add all the x components. Of course, gravity and the normal force have 0 x components, so I'm just gonna skip those zeros and jump directly to the components for the vector p. The px component here is going to be p cosine theta, and then I have to add to it the x component of the frictional force, which is minus mu Fn, and that has to be equal to the mass of the book times the x component of its acceleration. The problem is that I don't know the normal force. So before I can actually get to the x component for the acceleration as the book slides across the ceiling, I need to figure out what the normal force is. And that will come from the relationship between the y components of the normal force and the acceleration. Remember, the sum of all the y components have to add up to mass times the y component of the acceleration. Given that the book is sliding across the ceiling, but it's not breaking it, it's not changing its vertical motion, we know that the y component of the acceleration will be 0. So this here is going to be simply 0. So my equation here, let me write all the components. I will have first the y component of the gravitational force, which is minus mg. Then I have to add the y component of the normal force, minus Fn. The frictional force will have no y component, so I'm going to skip the 0. And I'm just going to write the y component for the pushing p force, which is plus p sine theta. And that has to be equal to 0. So this I'm going to turn into an equation for the Fn by moving the Fn to the right hand side here of the equation, and I will have Fn has to be equal to p sine theta minus mg. Or numerically, that will be 80 sine of 70 degrees minus 5, which is the 5 kilograms of the book, times 9.8, the value for the gravitational acceleration. I skip the units here for considerations of space, but here it is, the normal force, or the component, actually, the vertical component of the normal force comes out to be 26.175 newtons. So I'm ready now with that to go back to that equation for the x components, plug in the value for Fn, and determine what the x component of the acceleration of the book is. So let's write it here where we have some space on the right. I will start putting the numerical values of the magnitude of P and the angle. So I'm going to have 80 for the pushing force, 80 newtons actually, times cosine of 70 degrees, the angle between the force and the horizontal, minus 0.40, which is the coefficient of kinetic friction given by the problem, and times the normal force, which I just determined to be 26.175. And that all has to be equal to 5.0 kilograms, the mass of the book, times the x component of the acceleration. And so here it is, the x component of acceleration coming out to be 3.3784 meters per second squared. Remember, the acceleration is a vector, so every time when you get to the answer, you always have to either give both components. So here I either have to say AX is 3.3784 meters per second squared and AY is 0, or a more common and actually natural way for everyday life situations is to actually give the magnitude of the acceleration. In this case, it's very easy. We don't have to use the Pythagorean theorem. Directly, we can see directly that the magnitude of the acceleration will be 3.3784, or here I can actually round it because this is going to be my final answer. So here the standard 3 digits, 3.38 meters per second squared, and I have to also give the direction. So I have to indicate here that the acceleration has this magnitude of 3.38 meters per second squared, and the direction is to the right. So that is our answer to the question of this problem.